Hello, welcome to this lesson on simple alkyls or alkyl substituents. The question of the day, what is the same about these two molecules and what is different about them? There are a ridiculous number of organic molecules. There are far more organic compounds and molecules than there are inorganic compounds. So the reason for this is because carbon is a little trickster. Not only can it make chains, rings, and networks, but also you can stitch carbons on top of carbons. So if you have a big old carbon chain, you can stick other carbons on top of that. So because there's just so many combinations of how carbons can bond to each other, we have an entire branch of chemistry called organic chemistry, and those little things that dangle off of the carbon chain are called substituents. Today we're going to be talking about carbons dangling off of carbon chains, but you can also have a slew of other atoms dangling off of this carbon chain. So those generally are called substituents, but because we're talking about carbons dangling off of carbon chains, those are going to be alkyls. So here you can see that we have a carbon, specifically a methyl group, dangling off of a 4-carbon chain. Naming these things is just one step more than naming your typical alkanes, alkenes, and alkynes. In this case, you're still going to be looking for the largest string of carbons that you can get in a row without picking up your pencil, skipping over, and continuing, or without going through and then doubling back and then making a new path. You can't do that. You need the longest string of carbons that you can get in a straight line. Although on paper they can bend around. Just a line with your pencil. Then what we need to do is find all of these things that are dangling off of the carbon chain. I like to call them dangles, but typically they will be called substituents by people who use proper language. We are still going to count the number of carbons forwards and backwards because we want our numbers that we assign to these dangles or substituents to be the lowest number possible. Now, sometimes you'll have more than one thing dangling off of this carbon chain, so in that case you would want your substituents to receive the lowest sum possible. So sometimes it'll be best to give your carbons higher numbers per se, just because the sum of the two numbers that you get is the smallest possible. So instead of having a 2 and a 3, you might want to name them a 1 and a 3. That doesn't make sense. The more substituents you have, the more that makes sense, but for our purposes, it probably won't come up very much. When we're talking about carbons dangling off of carbon chains, we are still going to use their carbon prefix, so meth, eth, prop, bute, pent, hex, and so on. And then we're going to tack a YL ending on that to indicate that it is dangling from the main chain. All of our dangles or substituents are going to be listed in alphabetical order in the name, regardless of the order in which they appear numerically on the carbon chain. So for instance, an ethyl will always come before a methyl because E comes before M. But if you look at the carbon chain, your methyl might be on the 1st carbon and your ethyl might be on the 4th carbon. But their location does not matter when we're talking about the names. For the names, we are going to list them alphabetically. So here is that compound from earlier in the slides. And the question is, what are we going to name this thing? Here we have a string of 4 carbons, and it doesn't really matter how you view these 4 carbons. Most of us are just going to see these 4 carbons running in the straight line. Some of us will see that this carbon chain bends. So you would count these 3, and then this would be the 4th one, or this could be the 1st, and you count this way. No matter how you count it, you go through and label, you can get 4 carbons in a row. And from there, you will find that you will have a 1-carbon mini chain dangling off of the main carbon chain of 4. And that chain has that carbon, the 1-carbon dangle, which we would call a methyl. 1 carbon is meth, and the YL tells you that it is dangling. So we would have a 1-carbon dangle on the 2nd carbon of our chain. So for that reason, we would call it 2-methylbutane. We have a 4-carbon chain, so we would call it bute. It's all single bonds, so the base would be a butane. On the second carbon, we have a 1 carbon dangle. So on carbon 2, we have a methyl group dangling off of the main chain. See if you can figure out this one. 3,2-ethyl methyl pentane. Your carbon chain may not look exactly like mine, but we should both have a 5 carbon main chain. This 3 is assigned to the ethyl. So on the third carbon, we should have a 2 carbon dangle. So 1, 2, 3, my third carbon, or you can count from the right, 1, 2, 3. I would have a 2 carbon dangle. So I have CH2 and then a CH3. That's 2 carbons in that substituent. That would be the ethyl group. Now the methyl group has to go on carbon 2 because the 2 is going to correspond to the methyl. Now I could have put my my 1 carbon dangle, my methyl group, on this carbon here, or I could have put it on this carbon here, one or the other, not both, because then it would have to be a dimethyl, indicating we had 2 methyls. So here on the second carbon, you have to have the 1 carbon dangle. It's clear here that I have numbered my carbons from left to right. So this one all the way on the left would be carbon 1. This is carbon 2 with the methyl, carbon 3 with an ethyl, carbon 4 and carbon 5, chain of 5 giving me the pentane. Getting back to that question of the day, we had 2 molecules that I hope you figured have the same chemical formula, although they are built entirely differently. And those are chemicals that we would call isomers. I like to think of them as cotton. This sounds a little bit weird, but if you go rummaging through your closet, you may find that your socks are made of cotton, your denim jeans are made of cotton, and you may have cotton t-shirts. All of those are made of cotton, but the cotton is going to be built a little bit differently, a little thicker in some fabrics than in others. And that is kind of like an isomer. They're made out of the same stuff, but built a little bit differently, so they will have different properties. In the case of your clothes, you may have things that are a little bit more durable, or maybe some clothing that's a little bit more soft. Think maybe your pajamas versus your jeans. Those are going to be 2 different forms of cotton. And that's kind of what's happening with isomers, that we have different arrangements of the same number of carbons and hydrogens. And in doing that, they will have different properties. Pause the video and take a minute to draw these 2 molecules. This right here is a molecule of butane whose chemical formula is C4H10. We have 4 carbons in a straight line, all single bonds, and the boiling point of butane is -1 degrees Celsius, meaning that you would find it as a gas at room temperature. And here we have 2-methyl propane. So here our chemical formula is still C4H10. The boiling point is a little bit lower at -11 Celsius. And you could see that this molecule is far more crowded than the straight chain of butane. In this molecule, of course, these bonds are going to spin and kind of turn in 3 dimensions. Single bonds are kind of wiggly. But in the case of 2-methyl propane, you have a big methyl group kind of crowding this entire molecule. So even though it doesn't necessarily look like it, that carbon and its hydrogens are going to just put a lot of, we call it steric hindrance. It really just means there's a lot of stuff in a small space. So this molecule, because it's a little bit more crowded, is going to have different chemical and physical properties than its isomer, butane. They look the same. They are made of the same stuff, but they do not look the same. They look different, and as a result, they will have different properties. We kind of got into this a little bit with one of the examples, but carbon chains can have multiple dangles or multiple substituents. And this gives organic molecules a lot of variety, and it's a huge reason why organic chemistry is an entire branch of chemistry, just because there's so many combinations. So sometimes we'll have more than one thing attached to the main chain. In this case, the longest chain that you can get is 3 carbons, so that would be a propane. And on that propane, we have 2 methyl groups attached to carbon 2. Now, if you look at this picture, It does not matter if you look at it vertically or horizontally. The longest chain you can get is 3 with 2 methyl groups on either side of carbon 2. Like I mentioned earlier, when you have multiple substituents, in the name, their names will be alphabetized regardless of their numerical location on the carbon chain. If we have 2 substituents attached to the same carbon, like we had in our example, you would list the number twice. So you would have to say 2,2-dimethyl propane. Kind of obnoxious, but that's the way that it works. And then we would use a regular covalent prefix to indicate the number of identical substituents on that carbon chain. So that's why we would have that dimethyl, 2 methyl groups. This is another example. Here we have a chain of 6 carbons all single bonded to each other, giving us hexane. And on that hexane, we have 2 methyls. They are on the same carbon. So we'd have to list 2 twice. So 2,2 tells us we have the dimethyl, the 2 methyls, each on carbon 2. A lot of 2s. Now, the di prefix does not necessarily mean that they are on the same carbon. It just means that there are 2 of them. So in this case, we have 2,3-dimethylhexane. So again, the 6-chain carbon, all single bonds. Then we have 2 methyls. That's where the dimethyl comes in. And you will find one of them on carbon 2 and the other on carbon 3. One final example. Here we have heptane, which is a 7-carbon molecule. And the ane in heptane tells us that they have all single bonds connecting them. Then we have 3,2-ethyl methyl on this heptane. So 3 will correspond to ethyl. So on the 3rd carbon of this chain, you will have a 2-carbon dangle. And on carbon 2, you will have a methyl dangle. So a 1-carbon dangle. So here there is no di prefix because ethyl and methyl are 2 different things. We have 1 of each. And then the dangles or the substituents are alphabetized regardless of their numerical location. So it looks like it's kind of silly to say 3, 2, but in organic naming, based on IUPAC rules, we want our substituents to be alphabetized, again, regardless of their numerical location. So this is everything on alkyl substituents for high school chemistry. There is a lot more that you can do, but truthfully, you're only going to learn this by practice. So make sure to get your practice, answer the questions that the teacher gives you because they are important for your learning. Leave any questions you have in the comment section below the video. I would be happy to help you. Subscribe, please, so you don't miss the next lesson, and I'll see you there. Bye.